Okay, let's go ahead and get started with today's lecture. So today we're going to be wrapping up our reinforcement learning portion of the course. And so let's go ahead and just jump into some announcements as always. Just a reminder, please do complete the final course evaluation. Really important that you guys fill this out. It's due in about 9 days, so you have some time, but please do this. So far, 30 of you have filled this out. I think there's hopefully more than 30 students of you in the audience right now, so please do actually fill this out. Upcoming deadlines, fifth homework is due in a week, so that's due next Friday. And the project is also going to be due in about 1 week, so the Monday of finals week. So 2 deadlines coming up pretty quick. And then just a heads up, next week's lecture topics are going to be these so-called advanced topics that won't be on the final exam. So by the end of today's lecture, you guys will have seen everything that's going to go into the final. But my plan for these advanced topics lectures are to Monday cover some natural language processing. So things like how do language models work, things like GPT-3. Going to be very high level. We can't, of course, get into all the details of NLP in just one lecture, but should hopefully be interesting. And then on Wednesday, I was going to cover generative models, particularly for image data. So if you guys have heard of things like generative adversarial networks, or GANs, and diffusion models, the plan was to give a really high-level overview of how these models work. So pretty high-level stuff next week, but hopefully should be interesting things, so definitely do attend. And then on Friday's lecture, we're going to just do a final exam review. There will be a sample final that I'm still working on, hoping to get out to you guys pretty soon. But that'll be a good time for you to come with questions about the final exam and also reviewing that sample final. Okay, so in today's lecture, we're going to briefly recap what we've seen so far about reinforcement learning, kind of just the key definitions that we need to know going forwards. Then we're going to introduce these Markov decision processes, which again are this mathematical framework for doing reinforcement learning. So all RL problems are really kind of built on these MDPs. And once we finally know what an MDP is, how to work with these, we'll start seeing finally some ways that we can actually do learning in these types of problems through some methods called policy evaluation and policy improvement. Okay, so let's get started with the review of what we've seen so far about Markov processes. So we saw in a previous lecture the notion of a Markov chain or a Markov process. It's just some collection of states with transition probabilities between them. And then we introduced the notion of a Markov reward process, where rather than just having states and transition probabilities, we also introduce a reward function, R, that tells us what's the reward on average that we get by entering some state S. So R sub S is on average, what's the reward I get from going into that state? And these Markov reward processes also have another associated variable here, this gamma variable, which is a discount factor. It tells us how much we should discount future rewards with respect to current rewards. Okay, so we saw this all in a previous lecture, but good to have it fresh in your mind. We also introduced the notion of a return. So a return, G sub t, is not just the reward that I see in the next time step, but it's the total discounted reward I see by sort of following my Markov reward process for infinitely many steps into the future. Again, it's the sum of the next reward I get plus the discounted reward I get after that, and so on and so forth. And really we're interested in modeling these Markov reward processes in order to obtain high rewards. So rather than just getting high returns, we want these G's to be large. Okay, and we also introduced the notion of a value function. So a state value function, V of S, takes in a state S and returns a number to us. And that number tells us how valuable it is for our agent to be in that particular state S. And sort of formally what this is it's the expected return of being in that current state. So on average, if I enter the state S, how much reward am I going to see after a long time horizon from being in that state? So really these are the key definitions we've seen so far about Markov reward processes. What we're going to do now is start introducing actions into these setups. So once we have actions, once we have an agent that can decide what to do next, we're going to obtain these Markov decision processes. So I've shown this graphic probably 10 times now, but we'd start with Markov processes and add rewards to get Markov reward processes. And today we're going to add these actions to get Markov decision processes. Okay, so Formally, a Markov decision process is a Markov reward process, so we start with the same definition we had before. But we're going to go ahead and add a finite set of actions to that previous tuple. So here, this script A represents some finite set of actions that my agent can take at every time step. Our setup changes a little bit now, though, in that our state transition probabilities, i.e. if I'm in some state and I take some action, what state am I going to end up in next? Well, the state transition probability matrix depends also on the action that I take and not just the current state that I'm in. So in general, we have one matrix, one transition matrix, for every single action that I can take. So that's what that superscript A here denotes. It's what action I'm taking. I'm getting out some transition matrix. In general, even though you take an action, you don't necessarily deterministically transition to some new state. So for example, I might have some state I'm in. I might say I want to try to turn left, but there's maybe a 10% chance my steering wheel breaks and I accidentally go right or something like that. So just because I decide to take an action doesn't mean my next state is going to be deterministic. So we still have this transition matrix of probabilities. And we also have a reward function. It's the same thing we saw before, except this reward function depends not only on the state that we're in, S, but also on the action that we take. So our rewards depend on both our states and our actions now. And then we've got a discount factor gamma, just as we saw before, telling us how much we value present rewards versus future rewards. So again, we have the same sort of setup. We have states and rewards, except now we have actions associated with each time step. A policy, pi, is going to be some function that takes in a state S and returns a distribution over the possible actions that I can take. So my function, my policy pi, if I give it an action A, it's going to tell me how likely am I to take that action A given that I'm in the current state S. So it's what our agent is deciding to do. Here we're writing this as a probability, but this lets us capture both deterministic and stochastic policies. So if I have a deterministic policy that says whenever I'm in a particular state, I should take some fixed action, well, the probability for that action will just be 1, and the probability for other actions will be 0. So even though I've written this probabilistically, it captures kind of both of those settings. And really, these policies fully define the behavior of any agent that we're working with. It tells our agent what it's going to be doing. In a Markov decision process, the policies are assumed to depend only on the current state S, not the entire history of states. And this is what makes it a Markov decision process. Again, remember, Markov means that we only kind of consider the current time step and not the full history of time steps. Another way of looking at this Markov assumption is to say that policies are stationary or time independent. So it doesn't matter what time step I am at in my process, I'm going to have the same policy. It only depends on the current state that I'm in. Okay, let's see an example with this student Markov decision process that we've seen a few times. Again, our states are classes in here in the middle. We've got a sleep state, we've got a Facebook state up here, and we've got a pub state down here. Our actions now are what our student is going to decide to do when they're in a particular state. So if in this first class, C1, there's 2 actions that the agent might decide to do, which is either go to Facebook or study and go to their second class. For this particular state, your actions are deterministic. So the student, if they decide to go to Facebook, well, there's a 100% chance that we'll go up to this state. Or if they decide to study, there's a 100% chance they'll go down to this state. However, this state down here, the pub state, our actions actually result in stochastic transitions. What I mean by that is that if I'm in the pub and I decide to study, well, there's maybe only a 20% chance I actually study, or rather, sorry, let me back up a second. If I'm in my pub state and I decide to take the action study, well, there's maybe a 20% chance I study for class 1, a 40% chance I study for class 2, and then a remaining 40% chance that I study for class 3. So what action I take can actually result in sort of stochastic transitions to a random state. But this random state can depend on the action that I take, of course. Okay, so now let's introduce a new notion called a state value function. It's essentially the same idea as a value function that we had seen previously that tells us kind of how good it is for us to be in a particular state S. but now the state value function is going to depend on our policy pi. Again, this is going to depend on our policy because the policy determines what states we're going to enter. It tells us what actions we're going to be taking. And so the expected long-term reward of being in a particular state, of course, depends on this policy. So again, we've seen this notion of a value function, but now it depends on our agent's policy. And a new notion here is that of an action value function, sometimes just called a Q function. This is really standard notation. And what this Q function does is it takes in a state S, and it takes in an action A, and it tells us kind of how good is it for our agent to be taking that action when it's in that particular state. So it's what's the value of my agent behaving in a certain way. Formally what this is it is the expected long-term reward, so it's the average long-term reward, of my agent being in state S and taking action A. So again, it's somehow evaluating how good it is for our agent to take this particular action. Okay, so any questions on the new definitions we've introduced or any of the stuff we reviewed? Yeah. Yeah, so the state value function just tells us if I have a particular state, how valuable is it for me to be in that state? In contrast, the action value function looks at what state I'm currently in, and it looks at that action A that I might choose to take and tells me how good that action is. So the difference is just V tells me how good a state is, the action value function Q tells me how good a particular action is at a particular state. Yeah. So the value function, as we saw previously, there was no policy. It's essentially the same exact concept, except the state value function depends on the agent's policy. Because the agent's policy is going to tell me, okay, if I'm in a current state, what future states I end up in, so it will affect my long-term reward. So if I have different policies, even if I have the same underlying Markov decision process, well, it's going to result in different values for particular states. Okay, any other questions on these? Now's a good time to clarify them because we're going to start making these more complex. Okay, great. So as we saw before, there are these things called Bellman equations. In general, kind of, if we only know our underlying Markov process, we don't know the values of the states, and we don't know that Q function either. So V and Q are unknown. We're going to need to compute these somehow. And one way to do that is via these Bellman equations, which give us recursive relationships between the values of our states. So we saw exactly this equation before when we were computing the values of states in the second lecture on RL, except now things depend on the policy pi. So it's just this recursive relationship that we can actually go ahead and solve in closed form for the value of a particular state. Okay, I'm kind of skipping the derivation here, but take me at my word that the value of a state is indeed the expected reward plus the discounted value of future states. Similarly, the action value function Q can be decomposed in essentially the exact same way, where the value of taking an action at a particular state is the expected reward I get from that state plus a discounted version of the expected value of taking future actions in future states by following my policy pi. So it's essentially decomposing the value of a state action pair into my current sort of reward plus the future rewards I would get from following my policy and evaluating their state action values. Okay, so let's draw this diagrammatically and write down some equations. So what I'm doing here is for white nodes, I'm indicating states in my Markov process. And by the filled in dark nodes, I'm indicating actions. So generally, I enter some kind of state, and then I take some kind of action depending on that state. So I start in the state S, and there's maybe two different actions I can take in this state, indicated by these two black dots. This state has some particular value, V of S, and each of these actions has some particular value, Q, that depends on the action we take, but it also depends on the state S. So we're evaluating this Q function for this kind of particular rollout. And what you can do is if you kind of crunch the equations, skipping the derivation, you can actually write the value of being in a state S in the following form, where it's a sum over all the possible actions I can take in that state of the probability of taking that particular action according to my policy. So how likely am I to take the action A, times the value of taking the action A in the state S. So in other words, to get the value of a state S, it's just the average value of all the actions weighted by the probability of me taking that particular action. And yeah, question? We will, eventually. So this is for a particular policy, and we'll eventually want to find the optimal policy, but this is just saying if you give me a policy pi, you tell me how my agent acts, I'll tell you how my value is for each node. Okay, so nice formula lets us compute the value of a state if I know my policy pi and if I know my Q function. But as I said, we don't know these values, we don't know the V function, and we also don't know the Q function. So this is kind of useless for us, we don't know these two things on both sides of this equation. But we'll eventually see how to solve this. Let's do something really similar now, except kind of flip things around. So let's say that I'm in a particular state and I take a particular action. So that's the black node I've got here. And it has some value Q associated with that state action pair. Well, based on the action I take and the state I'm currently in, I might end up in multiple different future states. And those are indicated by the white circles down here. And here I'm just drawing two possible future states. Well, it turns out I can do a similar kind of backup equation, or sort of recursion here, where the value of me taking a particular action at a particular state is the expected reward I would get from taking that action. So what reward do I get on average from taking that action? Plus a discounted version of the values of my successor states. So in other words, it's the reward plus what's the average value of my successor states. And I'm taking an average here because I'm summing up the values times their corresponding transition probabilities. So again, I'm just decomposing my value, Q, of a state action pair into sort of the value of my future successor states. So comparing this to the previous equation, we've got V on the left-hand side and Q on the right-hand side. Here we've got Q on the left-hand side and V on the right-hand side. What we're going to do now is we're going to take these two equations that we just saw, just smash them together. And in doing so, the Q function totally drops out of our equation. So I'm taking, I'm taking this equation here. I'm taking Q sub pi, which I know how to compute based on this slide, and I'm just plugging it in. But what you should notice now is that I only have one unknown in this equation, which is my V function here. So I don't know V, but I do know the policy pi. I know my rewards. I know my discount. I know my transition probabilities, but I don't know V here again. So what I can do is I can write this in a matrix form, which I'm not going to show you. And in doing so, you can eventually solve for the value of a particular policy pi. So this is really similar to what we had done before, except now we also have actions in the mix. And of course, playing the exact same game, we can also do the same thing for the Q function, where if we know the rewards, we know the policy, we know the transitions, then we can actually compute the Q function for a particular policy. So, in other words, given a policy pi and given some kind of Markov process, it's relatively straightforward for me to actually go ahead and evaluate them, i.e. tell me the value of a state and tell me the value of an action. However, in reinforcement learning, this is not what we want to do. We don't want to say, give me a random policy, I'll tell you how good it is. What I want to do is somehow find the best policy. What should my agent do to maximize the value of its rewards? And that's where we're going to go next. So I'm going to introduce a new definition here called the optimal state value function. Call this V star. And what V star does is it takes in a state S and it says, what is the maximum value of that particular state over all possible policies? So again, the value of a state is highly dependent on the policy that our agent is using. And if I choose the best policy for my agent, well, what is the best possible value for that particular state? Similarly, we can introduce the notion of an optimal action value function, which I'll call Q star. And this is the same thing, essentially, except instead of looking at the v function, we look at the q function. So q star of a state S and an action A says, okay, if I find my best possible policy for my agent, what is the highest value for that state action pair? So it's kind of like, maximizing this q function in some sense. And in fact, if we find q star and if we find v star, so we actually solve these maximization problems, well, then we've actually solved our Markov decision process. And what I mean by that is that if I know q star, i.e. if I can tell you what the optimal value of q is for a particular state and a particular action, I can actually tell you what the best action to take is. So I can kind of back out from this q star thing what the optimal policy is. Okay, there's lots of symbols on this slide. Don't worry too much about formally what this is saying. But all it's saying is that the optimal policy, pi star, the best action to take at a particular state S, is the action that results in the highest value of this q star function at the particular state. So what action has the highest value? Should intuitively make sense. If we find the highest value possible for an action, we just need to take the action that gives us that value. It turns out that there's always a deterministic optimal policy for any Markov decision process. So there's some fixed action our agent should be taking at every state that's going to maximize its long-term reward. And so as long as we know this q star function, if we can somehow solve for it, well, we can immediately write down an optimal policy based on this optimal value function. Okay, let's see an example. So here, the q stars indicate the actual optimal value of taking particular actions at particular states. And the highlighted red arrows indicate the optimal actions for our student to be taking. So if we're in this state corresponding to the first class, well, the q star of taking the action Facebook here is 5. So the optimal thing I can do if I go this direction is only sort of 5 points of reward. But if I study, I get 6 points of reward. And so since q star here is 6, is larger than 5, the optimal action for my student to do is to study. Similarly, I should study if I'm in my second class. Then once I'm in my third class, I should, again, study and eventually go to sleep rather than going to the pub. So again, I've computed these q star values, which I haven't told you how to do yet, and these tell us the optimal policy. It's whatever action results in the highest reward. Okay, so how do we actually compute these optimal values of v star and for q star? Well, we have similar Bellman equations, essentially relating these values of v and q together. What this one says is that the optimal value for a particular state is actually the maximum over all possible actions I can take of the state of this q function. So again, the q function tells me what's the value of taking an action at a particular state. Well, the best possible value for a state is what's the best possible action I can take at that state. So this should make some intuitive sense, hopefully, relating v star and q star to one another. But this again assumes that I know what q star is. But if I do know q star, well, it's straightforward for me to compute the value of being in a particular state. Again, skipping details on the derivation here, you can write down a recursive relationship for this v star equation. It's really similar to what we had seen before, where there are some rewards on the right-hand side and some transition probabilities, and v appears again. But the problem here is this is actually a nonlinear equation. So unlike the equations we saw for a particular policy pi, which are fairly easy to solve, the optimal state here has a maximum involved with it. And so there's no straightforward way for us to actually solve this equation for v star. In fact, most of reinforcement learning is focused on essentially this one equation here, trying to find the optimal value for every state in our process. Okay, so that wraps up Markov decision processes. We've seen kind of all of the tools we need to actually formalize and build reinforcement learning problems. And so do we have any questions on what we've seen so far? Okay, so let's actually see our first reinforcement learning algorithm, unless you count multi-armed bandits, and that is policy evaluation and policy improvement. Okay, so before we get there, I'd just like to give you an overview of what RL problems really look like. So we've seen Markov decision processes, which in general model states, transitions, actions, and rewards. And these again give us sort of the mathematical foundations for doing RL. But now that we have this foundation, what questions can we ask? What problems can we actually solve? And generally, RL problems kind of fall into two distinct camps. The first are prediction problems. So if I'm given a policy, I want to estimate the state and action value functions for that policy. So you tell me what my agent is doing, and I'll kind of evaluate that agent. These are often called prediction problems. In contrast, a control problem is one where you actually want to estimate the optimal state value functions. So rather than given a policy, I kind of want to find that optimal policy. There's kind of a sort of tension or a back and forth between these two, as we'll see in a few slides. There's sort of another class of RL problems, or another way of setting up problems, which is asking ourselves whether the underlying Markov decision process is known. I.e., do I know all of the states that I can enter? Do I know all of the transition probabilities? Do I know the rewards I'm going to get in every state? If yes, if we actually know sort of the underlying mechanisms of our environment, well, then our agent is just planning. There's no sort of exploration to do in the environment. It just needs to figure out the optimal policy. In contrast, if you don't know everything about your environment, this is often called model-free RL. We don't have some sort of model of the environment or of the world. And in this case, our agent actually has to sort of observe the environment and explore as it goes. And as you might imagine, the second setting here, model-free RL, is much more difficult than the first setting. And so lots of recent work in RL has been focused on this model-free setting. But yeah, of course, makes it much more difficult. So this kind of breaks our RL world down into 4 quadrants here, where you might know the underlying process and you want to evaluate the policy, or you might know the underlying process and want to find the best policy. Or if you don't know the underlying process, you don't know what your environment looks like, well, there's methods here that we won't have time to get into, like temporal difference learning and Q-learning, but good to have heard these words in case you take a future course in RL. Today we're going to talk about policy evaluation and policy iteration. So we're going to assume we know the underlying Markov decision process, we know the transitions, and we're just going to see how to evaluate a policy and how to use that to find the best policy. Okay, so we're going to see a technique called iterative policy evaluation. So I'm given some policy pi, I know how my agent behaves, and I'd like to figure out what's the value of all the states in my Markov process under this given policy pi. What we're going to do here is an iterative approach where we're going to repeatedly use these Bellman backup equations to eventually estimate the value of every state in my Markov process. So I'm going to get a chain or sort of sequence of values. Each one of these, v sub 1, is actually going to be a vector corresponding to the value of every particular state at a particular iteration of this process. And each iteration of this process looks like the following. So for every state in my underlying Markov process, I'm going to update to a new sort of estimate of the value of that particular state from the state in the previous time step, where S prime is the successor state of S. Okay, the difference here, let me show this equation. In other words, what I'm going to do is I'm going to iterate for a large number of iterations, this following equation, where my value of state S at iteration k plus 1 of my algorithm, I'm going to just plug into this Bellman equation that I had previously. So I showed you guys this before. Except the value v on the right-hand side is not going to be the value at iteration k plus 1. It's going to be the valuation at the previous iteration. So we're essentially going to write a for loop where we update the left-hand side of this equation over and over again. What's going to happen is that the left-hand side of this equation is eventually going to converge actually to the true underlying value for the policy. So we have an iterative way of estimating these policy values. Okay, you could also write this as a matrix equation down here, where the vector of values for every state at iteration k plus 1 is my rewards from following the policy, plus a discount times the transition matrix times my values at the previous iteration. Okay, kind of glossing over the details here, don't worry too much about it. But let's see an example. So this is a really tiny RL problem called grid world. So in grid world, we have, a grid of potential states here, where the goal is for our agent to navigate to these gray squares at the top left corner or the bottom right corner. So here I'm not using any discounting, because all my states are going to eventually terminate. And on every step my agent takes, so I'm going to randomly initialize my agent in one of these white squares, and in every step my agent takes, it's going to get a reward of -1. So the goal of my agent is to, as quickly as possible, make it from its starting white square onto a gray square. At initialization, my agent is just going to follow a random uniform policy. And what I mean by that is that my agent at any particular time step is just going to randomly move either up, right, down, or left. So not a very smart agent. What we would like to do is that under this policy, we'd like to evaluate what's the value of being in any one of these particular states. So for each square, I would like to associate or compute its corresponding value. Okay, so at k equals 0, I'm just going to essentially fill in a value of 0 for every one of my states. So I don't know what the value for these states are yet. I'm just going to have some initial guess. After one iteration of that update equation I showed you before, what happens is that I get a value of -1 for all of my sort of internal nodes, the ones my agent can walk on, and a value of 0 for these nodes on the outside. After k equals 2 iterations of this, I update my values again for the states in this recursive way. And what you can see is that kind of slowly what's happening is that the squares closer to our ending states, our goal states, are getting higher values than the squares that are kind of in the middle. So our agent, what it should do is it should seek out these high value states. And in fact, if you follow a greedy policy with respect to the values of these states, what I mean by that is that if my agent is in a particular square, it should move to whichever of its neighboring squares has the highest value. You get a policy that is going to essentially follow these valuations. So again, I start with a random policy where no matter where my agent is, it's just going to randomly move in some direction. But once I update the values after, say, one step, well, if my agent is in either one of these squares, what it should do is move to the highest value neighbor. So here I start with these -1 values. I've got a 0 here. My agent should move towards the 0. So that's what these arrows are indicating. If I do this for one more step, well, you see my agent kind of knows a bit better what to do next. And if I keep iterating to estimate the optimal value for this original policy, well, eventually I'll actually find the optimal policy for this agent to take, where it just moves in the straightest line possible towards those end goals. And again, at convergence of this iterative procedure, my agent is valuing the states that are closest to the end goal much more highly than those states where it's kind of far away from them. So it tries to move away from these low value states. So in this iterative fashion, what I've shown you is that if you give me a policy, I can evaluate the value of my agent being in any one of those particular states under that policy. So I can evaluate policies, is my point. So any questions? Okay, so we've seen how to evaluate a policy through this iterative procedure. Now let's see how you can actually find the best policy. So my goal again is to find an agent, find the actions it can take. It's going to maximize its reward. Okay, we've actually got a really simple algorithm here called iterative policy improvement, where it really only has 2 steps. The first step is that given some policy pi, which I'm just going to randomly initialize, my agent takes random actions to start out with, I'm going to go ahead and evaluate that policy. So I'm going to use the iterative procedure I showed you before that takes in the policy and tells me the value of every state in my process under that policy. And then what I'm going to do is I'm going to improve that policy. And to improve the policy, what I'm going to do is I'm going to act in a greedy fashion with respect to v sub pi. And what I mean by that is that my new policy, which I'll indicate by pi prime, is going to be a new policy where my agent says, okay, no matter what state I'm in, I should choose the action that is going to result in me moving to the nearest neighboring state that has the highest value according to this v sub pi. So I value my policy, my agent takes the best actions according to this valuation. And then I just iterate between evaluation and improvement. So in our small grid world example that we saw before, we actually saw that doing this loop between evaluation and improvement actually resulted in us finding the optimal policy for our agent. In general, you're going to need a lot more iterations than just like 3 or 5 or whatever it was for the grid world example. But it turns out that this really simple policy iteration algorithm always converges to the optimal policy. So we've got a fairly simple algorithm here that actually lets our agents find the best actions. Okay, so we've got an illustration of this just to kind of drive the point home. We start with a random policy, we evaluate it, and then we improve it, we evaluate, improve, and so on and so forth. And eventually we converge down to the optimal policy. Okay, so any questions on policy improvement? Okay, let's go ahead and wrap up for the day. Be a bit of a short lecture. So we've essentially concluded reinforcement learning now, where we saw that most of RL is built on these Markov decision processes, which again model states, actions, rewards, transitions, and have a discount factor to them. Depending on whether or not this underlying MDP is known, your agent either needs to just find the optimal policy through planning, and we saw a really simple algorithm for doing that, this iterative policy optimization. But if the underlying MDP isn't known, we're in a model-free RL problem, which we certainly won't have time to cover in this course. Okay, and again, we saw that one strategy for finding optimal policies is to start with a random policy, evaluate it, and just iteratively improve by behaving in a greedy fashion. I'd also like to take a second just to point out that reinforcement learning is a huge, massive field, and we've really barely covered the basics in this course. So if you're interested in RL, despite all the mathematical formalisms you need to get started here, there are some courses here at UCI that you could check out if you want to learn more. Okay, and with that, we can wrap up quite a bit early today.